Welcome to the CFE Media and Technology Education Session, What to Know when Repairing Electric Motors. I'm your moderator, Mark T. Hosky, with CFE Media and Technology. For a seamless online experience, here are some tips. This session is set up in a linear progression, requiring attendees to view all in-course content before moving on. Additional resources can be viewed and downloaded on the left side of your screen below the session's agenda. If you would like to take notes within the session, click on the left panel labeled Notes to do so. This session is available on demand if you need to come back at any time. Please remember that this session has a live question and answer session at 10 a.m. Central, 11 a.m. Eastern. Watch the full presentation before the Q&A and get your questions answered by industry expert Tom Bishop. You can see the Q&A details in the Meetings tab on the left side of the screen. If you're interested in receiving one AIA CES approved learning unit for this event, you need to pass a 10-question exam and get at least 80% correct. In keeping with American Institute of Architects' continuing education system policy, please take some time to read the quality assurance slide. In keeping with our CEP policy, please take some time to read the quality assurance slide. Here is an overview of today's session. I'm not going to go through all of this in detail. The presenter will cover this during the technical presentation. Here we have a list of learning objectives. We'll touch on these in today's presentation. Please note that any red underlined text you see is a hyperlink to a reference or resource to guide you to more information. Additional resources can be viewed and downloaded on the left side of the screen below the session's agenda. Let me introduce today's speaker. Tom Bishop is a Senior Technical Support Specialist at the Electrical Apparatus Service Association, known as EASA. He joined EASA in 2002 with more than 30 years of hands-on and engineering experience at electrical machinery manufacturing and apparatus service firms. Tom has authored dozens of technical articles and papers, and presented numerous seminars and webinars on electric motor application, maintenance, and repair. In addition, he is chairman of EASA's Technical Services Committee and a principal member of the National Fire Protection Association Electrical Equipment Maintenance Committee, NFPA 70B. It's my pleasure to work with you today, Tom. Please go ahead.
Thank you, Mark. Okay, and welcome everyone. What we're going to be discussing today, the focal point is we see right here that word motor efficiency. So motor efficiency is related to things like repair, replace. We're going to talk about an EASA accreditation program and our recommended practice for repair. All these linking back to motors and being concerned about motor efficiency. And to go, let's call it further upstream, starting out with the motor itself. Motor manufacturers, they work to improve efficiency of the motors they build by design changes that reduce the losses in the motor. And the service center's goal, their objective, is to maintain the efficiency as built, and also, when possible, also increase the reliability of that motor by using good repair practices. And we see this little pie chart with the breakdown of the motor losses. These are the things that we want to keep that pie, whatever size that pie is. We don't want it to get bigger in any one area. We don't want any of those parts of it to start bulging out. So we have things like stator I squared R losses, which is that's current squared times resistance. It's power losses in the windings, and we see 35 to 40%. In other words, it's a big chunk. Rotor losses, rotor I squared R losses, another relatively large chunk. And the rotor and stator, they link to each other in the sense that what we're doing with the motor is we're taking electrical energy, converting it to mechanical, so the rotor rotates. And what that would be, if we think of it like a transformer, it's like a transformer that's going from static or standstill energy in the stator with a revolving magnetic field and turning it into a shaft that rotates through the rotor's magnetic interaction with the stator. So we have that. We're producing useful energy, useful work from that. And we have stator core losses to deal with. In order for the stator to work, we need a magnetic material to create the magnetic field, and that's the core. So another area that's, again, a big chunk of loss potential. I'm going to skip over stray load just to touch on friction and windage. Has to do with friction in the bearings, windage from cooling fans within and even external to the motor. And then the final area, stray load losses, that if we went back a century ago, the motor designers at the time, they knew by doing testing for motor efficiency that there was more to motor losses than what they could calculate. And they could measure it, but they couldn't calculate it because they really didn't know what it was. Today we have a much better understanding of what most of those losses are, but we still can't calculate all of them. And put it in simple terms, it's an interaction that occurs between the stator and the rotor in the air gap between them. And to look at a view of a motor here, we see what these, where these loss components are. Before I go into those, though, look at the formula we have at the top. Efficiency is input minus losses divided by input. Well, input minus losses, that turns out that's our output. So in the simplest of terms, energy efficiency is output divided by input. When we get into trying to measure, the load on a motor, not the load, but also the losses, losses are a very small part. So if we measure output over input, a big number over a big number tends to be not very accurate. So we'll discuss some things about, what these losses are to get a better appreciation of how small they are and what happens with them. We've got stator I squared R losses, and I'm going to try and turn on my little laser pointer here. We've got the stator I squared R in the windings of the motor, and then that's embedded in a magnetic steel core. So that's core, where we can have core losses. There's a core in the rotor with some losses there. The rotor also, again, rotating transformer, secondary. We've got an aluminum die-cast rotor, this is called. So we have aluminum end rings with bars in the magnetic material. So we've got rotor losses there. We have friction and windage. We see the fan, the external cooling fan. We've got the bearings. We also have internal cooling fans. And then we have this stray load loss that, as I mentioned, occurs in the space between the stator and the rotor. There's a slight clearance between the two. Core losses. The core losses in terms of repair, our concern is that the core losses, they can be increased if we distort the laminations. And if we see distortion like this, where the laminations aren't perfectly in a straight line, we start losing our symmetry, that can lead to losses. Excessive grinding. Here, there was some damage to the core and it had to be ground out. So there was grinding work that was done to that. And lamination insulation. These thin discs of steel we see here, they're less than a 32nd of an inch thick. So they're very thin, but they do have a coating. This picture shows some paint, but in between, when they stack this core, it's not paint. It's a special type of coating called core plate that goes on there. Microscopically small, but it is insulation. Another way that we have to be concerned in repair is we process these in a burnout oven, which is burnout as a misnomer. It's not burning the windings, it's heating the windings to a high temperature. We create thermal degradation. So these are the things that can affect the core losses in terms of what we're doing in the repair. The stator losses are what we call the I squared R, that current squared times resistance. We see a formula up here, the amp squared times the resistance, and that's a per phase resistance times 3 for 3-phase, which is the majority of the motors that we see in commercial buildings and industry. And we can, as a manufacturer or as a rebuilder, we can reduce the losses in the repaired product by increasing the wire area. The manufacturer can do the same if they change the design criteria. Also, reducing the length of the winding turns. The winding coils go through that magnetic core, and where there's a variable, it's where the windings come out of the core and go around and come back in. All of this area is not active. It's not inside a magnetic material. So we want to keep that to a minimum. If we reduce the length of the turns, then the R in the I squared R formula resistance, the shorter the turns, the less the resistance, similar to increasing the wire area. The larger the wire, the lower the resistance. I squared R loss in the rotor. It's the amp squared times the resistance of the rotor for the bars and the end rings. And here we see an example of a rotor without a core. Somebody has been able to erode the core away chemically for the purposes of showing us what we have here. So we've got these bars and end rings, and in this case, it's an aluminum material. Larger machines, it might be copper. So we have the different resistances and so forth, but we've got that. We've got these bars and end rings going through. And in terms of the repair, the rotor itself, unless there was a catastrophic repair, there wouldn't even be a call to change anything in the rotor. It just stays the way it is. It's not disturbed. And if there was a significant failure where the rotor, let's say, rubbed the stator core, for most motors, the vast majority, it wouldn't be economical to try and repair the rotor. Probably what would happen is either rotor is going to be replaced or a new rotor's it's going to be delaminated and relaminated with new bars and end rings. So again, rotor repair not normally change, rotor characteristics and the rotor itself not normally changed during repair. Friction and windage losses. We have bearings and friction losses in the bearings. We've got especially rolling element bearings. Bearing fits, the fit's too tight. That increases the friction losses. Over-greasing, too much lubricant, too much grease in the bearing, also increases friction losses. Fan size, if we've got a fan on the motor, a cooling fan, it needs to be replaced really exactly in time. We don't want to make the fan larger. It'll move more air theoretically, but that increases our windage loss. We make it smaller, it'll move less air, but then the winding's going to probably run too hot and possibly even the bearings. Blocked air passages, here's just an example of a motor where some of the varnish from a winding process got on the screen and started blocking some of those vent holes. So that would be a restriction in airflow. So we want to make sure we've got full airflow going through the motor or in the repair aspect. The stray load losses, things that can happen to the motor that affect the stray load loss. Smeared, in other words, if there was rubbing between the stator and the rotor, the rubbing on the stator core, that can increase the stray load losses. Same thing with the stray load losses being affected by the rub on the rotor. And uneven air gap. The rotor should be precisely centered in the middle of the stator. If it's off to one side, that's going to increase stray load losses. So that's our background to what it is about energy efficiency and what are the losses, what parts of the motor and how they're affected by the losses. Now we're going to move on to another topic with repair replace decision making. And what we want it to have is repair replace decisions that are made based on some let's call it hard evidence criteria. In other words, we want to make true decisions, and for that we're going to move in the next slide into a flow chart to provide an overview of the process. And it should be applied on a case-by-case basis. If we've got a motor that runs 24 hours a day and it's 1,000 horsepower, that's one kind of element or criteria. If we've got a 5 horsepower motor that only runs once a day, that's much less critical machine. We're going to apply a different set of criteria on that, judgmentally and economically and so forth. So a good practice would be to reassess the application as part of that repair replace decision. If it's a drip-proof motor, an open motor, and it's being used in a harsh environment, like maybe outside, subject to snow and wind and rain and so forth and dust, maybe we want to look at the possibility of taking that motor and not repairing it and changing it out, replacing it with a totally enclosed fan-cooled motor. A better approach, even beyond that, is taking the next step, if you will, is to do a assessing of the critical applications prior to failure. That if we've got, let's say we had a facility and we had 3 truly critical motors. Without any one of those 3 motors, the whole plant goes down. Well, those are the motors that we don't want to wait for the day when they fail to come in and say, we need to get a plan together. The idea is to have that pre-planned and say, if motor A goes down, here's what we're going to do. We're going to have a spare, or we're going to do this, or we know another plant that has a spare motor, we'll get it from them. Or we're going to tell the service center, work around the clock and get this thing fixed as fast as possible. We want that repair, don't hold up on anything, keep it going around the clock. So our flow chart. We start out with, here's a motor that's failed, and the first question we're asking, is it suitable for the application? If it's not, if it's that drip-proof motor that's in a harsh environment, we're going to investigate replacement with a suitable motor in terms of size and enclosure. You need the motor to replace the motor to fit where the old motor was. So we want to look at those things. And I'm going to jump down to this little bullet we have at the bottom. Additional considerations include increased reliability, life expectancy, benefits of additional features, upgrades or modifications. Those are some of the other elements that, whether we're going to repair it or replace it, we want to think about those as we go. Reliability, we want a new motor, maybe we want to put some type of a shaft seal on it to allow it to last longer in a water spray environment. If we're going to repair it, we want to do the same thing. We want to put some type of an additional shaft seal on it. So those are other considerations. So we've got this motor now, we're going to move this way down, and we're going to say suitable for the application. Yes, it is. Condition of the stator core. It's gone into the service center is evaluating it. We find damage that's showing high losses. And if we do that, if we find the high losses, then we say, wait a minute, is it going to be economical? We move down. Okay, we want to replace it. Well, are replacement funds available? Is there money in the budget? If there is, we go down. Is the replacement motor available? The new motor is available in stock at a supplier, or the new motor is 2 weeks away, but the application is such that it can be down for 2 weeks. So that would still be a yes. We move in lead time, and again, if that 2 week was okay, then we move down and we say replace the motor. What about if there's significant damage, but the cost of the repair, no, it's for a special motor. We've got that 1,000 horsepower motor. That's probably not on anyone's shelf. So we say, is the cost of repair greater than the cost to replace the motor? If it is, we move into replacement mode. If it's not, then we're going to move down into repair the motor mode. Going back to our left side, after we've assessed that core, we go through what about a catastrophic failure or evidence of prior catastrophic failure that's made worse by this failure. Significant damage, again, evaluate cost of repair versus replace. Damage to the rotor, if there's damage to the rotor, cost of the repair versus replace. And again, what I mentioned about any smaller machine, a NEMA style frame motor up to maybe 1 or 2 or even 300 horsepower. If there's significant damage to the rotor, it's probably going to move into the replace rather than repair mode, unless it's a special motor or the delivery time is way too long. So we've got this, we've gone through those, and we say, okay, it's gone through this, we haven't had anything. Let's say these are all no's and ok's. You come down to, is it an energy efficient or a premium efficient motor? If it's not an energy efficient or premium efficient motor, then we want to do an economic evaluation of the repair and say, is the repair on a long-term basis, assess the cost of energy versus the cost of repair over the expected useful work time, production time from that motor. We assess it, and if we say it's not going to pay off, we're going to repair. If it is going to pay off, we're going to replace the motor. So energy efficient and premium efficiency motors. What we mean by that is energy efficient motors. Energy efficient is a term from the U.S. Department of Energy's regulations that goes back to the Energy Policy Act of 1992. They were also called EPACT, E-P-A-C-T motors. That's our energy efficient motors. In the global world, the metric world, the International Electrotechnical Commission, IEC, the IEC designation for those motors is IE2. Then we have premium efficiency that before there was federal legislation, the motor manufacturers, NEMA, came up with what they called NEMA Premium. And these are now the premium efficiency motors with the metric equivalent global being the IE3 motors. So those are what we have, energy efficient and premium efficiency motors. The premium efficiency motors came about by regulation with the EPACT was 1992 with energy efficient, and premium efficiency was the EASA Act of 2007. And it's not EASA like Electrical Apparatus Service Association, EASA. It's EISA. It's the Energy Independence and Security Act. So that's the two types of motors that we look at today, there's still energy efficient motors, and premium efficient motors are basically they're the top of the line efficiency wise. So our repair considerations are the same really for all motors. They're the same for energy efficient, premium efficient, or older motors. We're trying to keep the efficiency level of the motor the same as what it was I should say when it was built, really, going back to day one. We want to preserve that. I don't want to say how it was received, because if the motor winding has failed, the motor that doesn't work really is basically zero efficiency. We can't use it. So efficiency can be maintained by qualified service centers, in other words, by doing good repair practice work. And where these good practices come from is from our recommended practice. It's ANSI EASA AR100, which is the recommended practice for the repair of rotating electrical apparatus. And it's further assured by participation in what EASA has as an accreditation program for service centers. And we'll talk more about AR100 and the accreditation program as we go through this discussion. So going back to the repair replace, consider the return on investment. The higher efficiency motor versus the lower efficiency motor, and factors that are involved. The lifetime of the motor or the process. How long is it going to run? What's the cost of energy? If we have a motor that runs 24/7, round numbers, it's about 9,000 hours a year. If that motor is going to run for 10 years and that application is expected to last 10 years, now we've got 9,000, we've got 90,000 hours. But what if we have a motor that's the same 10-year period, but it's going to run 8 hours a day, roughly 2,000 hours a year? Now we have about 2,000 times 10, 20,000 hours against 90,000. So our energy costs, for the same energy costs, that motor that's going to run longer is going to cost 4.5 times more, 90 divided by 20, 4.5 times more. So the one that's running the longer period, much more concerned about our return on investment because of what we're going to get paid back. Also, because we're going to get so much payback, it makes that evaluation process easier in terms of thinking about things like maybe we do want to replace an older motor with a premium efficient motor. And when we get that premium efficiency motor, we go out and we get bids on it and we look at the pricing. We want to look at the nameplate efficiency of the motors that are being used as the replacements, because one may have a higher nameplate rated efficiency than another. The U.S. Department of Energy regulations give criteria for what the nominal or average efficiency should be for a given power rating and speed. But even within that, that doesn't mean the manufacturer can't make something even more efficient than the standard requires. And there's a minimum efficiency, so they can be below that nominal or average efficiency and still be okay. It's acceptable. It's just, you can't build every motor as efficiently, let's call it, as you want. There's always going to be variations in production. But we look at those motors and we find one that says it's 95.3% efficient and one that's 94.9. We probably want to go for the 95.3 because we're going to gain 0.4 of a point of efficiency. And if it's going to run 90,000 hours, I'm sure that's going to add up to a lot of money over that period of time. So, other factor, new motor availability. If the new motor is available, premium efficiency motors in 2, 4, and 6 poles, 3,600 RPM nominal, 1,800 nominal, and 1,200 RPM nominal. Those motors are probably going to be off-the-shelf items. We get into larger motors or motors with special features. Now we can run into some, I don't want to call it issues, but they may have, not on the shelf, so therefore some delivery time associated with them. If the time exceeds the requirements for the customer, the service center can usually provide a good practice repair in less time than it's going to take to deliver that new motor. And they may also be able to add special features to a stock motor. Maybe they can retrofit it. Maybe the customer, the end user, needs to have a C face on the motor, and the service center can get a C face flange from the manufacturer and take off the normal end bracket and put the C face end bracket on the motor. So again, that's modification. So we may be able to, in the service industry, change that new motor into what the customer can use. So our accreditation program, moving out of repair replace into another topic, our EASA accreditation program. It is an international program for electrical apparatus service centers. So it's worldwide. There's a dozen countries now that have service centers with membership in the program. And it's based on electric motor repair good practices. So we've got these good practices that were identified in the ANSI EASA AR100-2015 edition, which, by the way, the 2015 is the current edition. And within a couple of months, we're going to be coming out with the 2020 edition, which, by the way, the good practices that were in there, they've been in there for like 10 years now. We haven't come up with any new practices that we can call additional good practices. It's a pretty solid environment as far as what we found that works for maintaining efficiency. The program evaluates the service centers for evidence of compliance, that there's a checklist, and then an auditor is going to go through and look at each of those items in that checklist. The service center does their own evaluation of that checklist to make sure that they have all of the equipment and all the practices in place to follow this program. And the scope of it, it applies to repair of three-phase squirrel cage induction motors. And EASA membership is not a prerequisite for participation in the program. So a service center doesn't have to be an EASA member. So anyone with a service center anywhere in the world can get into the accreditation program. The major processes that we look at: core testing and rewinding, bearing replacement, fit rebuilding, electrical testing, mechanical measurement. So we've got basically like a test and measurement, electrical and mechanical. Instrument calibration is also an important aspect to make sure, the measurement's not any good. You can get someone who can measure accurately, but if the device they're using for the measurement isn't accurate, then you don't have a good result. So conformance to the program, it's verified by independent and objective third-party auditors. And those third-party auditors, we have 7 firms that do that for the program. It rolled out in the summer of 2014. And right now we have 142 accredited service centers. External audits from the external auditors are supplemented with internal audits. And the internal audits have to be submitted to the external auditors for their approval. The checklist that is used has over 70 criteria items to it, elements. And we've got a label that can be put on the motor after the repairs are done. If it's a conforming repair, if it's met all the requirements of the good practices, then it gets labeled as an accredited repair. I'm not going to go through all of these checklist key categories here, but we have, just the top line. It's not directly into the repair, but training. The people who are working on the machines, there has to be evidence that they were formally trained. Internal audits, we mentioned that. Calibration, we mentioned that. Condition assessment, what's wrong with the motor, identify what happened. Shafts, bearings, and housings, we want to make sure that the shafts are straight, that the shaft bearing fits the journal, fit on the shaft, and the housing is good. The winding, a lot of attention to winding details, how the windings are moved, stator windings, what goes into the windings, and verifying the data, again, going back to that specification. And then electrical testing, high potential tests, no load tests of the completed machine. Example criterion used for test in the test descriptions. We have, this is the, item number 15 in the checklist, winding insulation and coil tests. And then the first criteria says stator winding insulation, resistance is measured, results are documented. So what's done is an insulation resistance test is performed. This applies a low voltage to the winding. The insulation resistance in millions of ohms or megohms is measured between winding and ground. It's the first test that's performed on the machine. If the winding to ground insulation is not good, then there's no point in doing other tests like a high potential or over potential test to ground or a surge test and so forth. It's already telling us that the machine is not suitable for repair. If we do and we get a good result, then it says move on and do some other tests. So we're determining the suitability of the ground insulation for further testing. The source document for the checklist, ANSI EASA AR100, its stated purpose, established guidelines, and each step of rotating electrical apparatus, rewinding and rebuilding. And by rotating electrical apparatus, it's not just motors, it's also generators. It's broken up into 4 major sections: general guidelines, mechanical repair, rewinding, which is the electrical aspect, and testing. Example here, and what we have with the accreditation program, and since it relies on AR100, the good practices from AR100. So what we're talking about here isn't just the accreditation program, but also some of the contents in AR100. So we have winding removal, core integrity. The picture we have here is a stator core with a very large, heavy wire going through it. And then this is the display from the meter. That's about 5.0495 volts, and that's over 2,000 amps. So we've got, a lot of a low voltage, very high current. And then this is the kilowatt, 7.2 something. So we've got over 7,000 watts of energy magnetizing the core, and we're testing for heating of the core. And also we measure that watts loss. And we can compare. The windings have been removed from this one. So this, let's call it 7.3. We'd compare that to the original incoming when the windings were still in it. And if it was 7.3 before and 7.3 after, we now have validated that we haven't changed the core losses. Stator windings, the as received winding date is verified, and we'll show something on the next slide about that. The insulation class, thermal capability equal to or greater than the original. So if it was 130 degrees C class B winding by manufacturer's design, the service center is probably going to go back with 180 degrees C class H design. The wire area per amp is at least equal to the original. In other words, we're putting in the same size wire so we don't increase the resistance losses. And example, and again, I'm not going through this card that we show a display of the output from a winding verification, but it gives us all the elements of what the winding design is about, what the characteristics of the winding are. And over here, we've got these magnetic flux densities that tell us whether or not it's a reasonable value. And we can verify the data. If it's a service center that belongs to EASA, they have access to our database of over 250,000 windings on file that they can compare what they found in that motor to it. If it's not on file, they may have a program like this to check magnetic flux densities, or as an EASA member, they can call us in our technical support group and have us check the data for them. The stator windings, copy rewinding. To maintain efficiency, we want to put the winding back and have it perform the way it was originally. This winding, if we look, you can see coils that loop around, and if you look closely, you can see where they go up and over inside. This means they have a common center, so it's kind of like an oval if you looked at it from left to right in the picture. We've got that shape, and the advantage of this for the manufacturers, these coils can be inserted by machine. Because they're inserted by machine, they can't get it quite as tight in the slots as you could by putting it in manually. And what many service centers do is they'll convert this winding, or have us in technical support convert the winding to what we call a lap winding, like what we see down below, where the windings, you lay a coil in and you lay the next coil in, and each one overlaps the next, so they don't have a common center. That's called a lap winding. Magnetically, it actually gives better performance. It has less losses, tends to be less noise than the concentric winding. And we can put more wire in the slots typically than the manufacturer can. And also keep the end-turn length controlled, keep it as short as possible. In terms of the rewinding, one of the options or availability sometimes, here we see a winding on the left. You can see all the black air spaces, lots of room for wires in between wires, or air in between wires, that we could fill in with copper, with more wire. What we do is we don't change the number of turns in the coil, the number of times the wire goes around. We use bigger wire. So now what we would get is just an example on the right. We see where the coils, the wires, we don't see much airspace between them. Because it's less airspace, bigger wire, we've got less losses from the larger wire and better heat transfer because there's smaller places for air pockets. Air is actually a good thermal insulator. So we want to minimize the air pockets, fill it in with varnish, but varnish isn't so good that it can fill large voids like that. And when we can go with larger wire, like the image shows, larger wire size, it's like a bigger pipe. We can put more water through it. we've got less losses by using a larger wire. Bearings. The replacement should be equal to the original or better suited to the application. If it's an open bearing, in other words, no shields or seals like this one, then we put back an open bearing. The service center, when I say we, I'm speaking from a service center perspective. If it has open bearings, as a service center, we might put a shield on one side. In other words, use one shield, a back shield on that bearing to help retain the grease in the grease chamber and prevent the grease from working its way through and finding its way into the winding, contaminating the winding and becoming a deposit that restricts heat transfer in the winding. So those are some of the options, some of the things to think about. We would not go to a sealed bearing because a sealed bearing is going to increase the friction. So the bearing fit to the journal and the housing, documented. Lubricant has to be compatible with the customer's lubricant. There's also a tag put on that says, here's the lubricant that we put in the machine, so we don't run into reliability issues because of mixed greases that aren't compatible. We reach the no load test. The machine's been assembled. We measure the voltages and currents at no load, vibration levels, check the mechanical condition, the acceptability when the job is done and someone's done all these tests, they say it's now okay to ship. Somebody has to say, this motor's ready to go. And then we apply the accredited repair label if applicable. So if it's an accredited repair service center, then they put the label on the motor saying, this is an accredited repair. We've maintained the efficiency on this motor. With calibration, we have the test instruments that are calibrated at least annually. Example here, some inside micrometers. And we see a label over here that's green and white. That's the calibration label. What we have up in the upper photo is a series of gauge blocks that are used. These are very high precision. So the micrometer is set up, it measures these that are of an exact known length, that are much more precise even than the micrometer. And that's part of the calibration process. Some service centers have this capability in-house. Some send them out to be calibrated. But that's what it is. All the instruments, mechanical as well as electrical, everything, the ammeters, the voltmeters, watt meters, they're all calibrated. So in summary, the accreditation program, the core elements, they're good practices, primarily based on ANSI EASA AR100, and they provide objective proof that efficiency and reliability are maintained during the process of repair and validated by objective internal and external audits. That the internal and external audits are going through and looking for, are we following, our steps? Are we going through each of those 70 plus steps and doing it the way it's supposed to be done? And in addition to that, the equipment that's used for each of those steps, is it calibrated, and is the calibration, record, does it show that it's, the calibration is current? And we're including mechanical rebuilding as well as electrical rewinding. Our big focus today has been, rewinding, and we're going to move on from here into the rewind study that was done. But rewinding is not every motor that comes into the service center for repair needs to be rewound. So those motors that come in with bearing failures or maybe a bent shaft and so forth, we're going to follow the same good practices all the way through the testing of the windings, even if they're not being rewound. We're going to do whatever tests we can on them to make sure that we've affirmed the integrity of that winding so that the motor goes back in and it maintains its efficiency and its reliability. In 2019, we performed a rewind study, and it was based on the question of, can premium efficiency or the metric IE3 motors be rewound without degrading efficiency? The precursor to all of this, when it was the days of the EPACT and the IE2 energy efficient motors back in the early 2000s, EASA and the AEMT got together, did a study then, and issued a report in 2003. And AEMT is the Association of Electrical and Mechanical Trades in the UK and in Great Britain. And what it did back then was prove that rewinding in accordance with good practices maintained efficiency, and that claims, what we've had now is claims in recent years that, well, the testing was done on the IE2 and the energy efficient motors. What about premium efficiency motors, the IE3 motors? Maybe something's changed. And as much as we didn't think so, we wanted to, quell that argument and, answer that argument by going back and doing a study on the premium efficient motors. So what we have is the same question. We wanted to determine if motor efficiency can be maintained when premium efficiency and IE3 motors are rewound, using the good practices from the 2003 study of energy efficient IE2 motors and using ANSI EASA AR100. And the reason for using AR100 is because it has the good practices that were identified in the 2003 study. Almost all of them were already in AR100, and following that study, they were incorporated into it. So by the time of the 2010 edition of AR100, all of the good practices had been built into the AR100 document. And the research that was to be done included independent third-party laboratory testing of the efficiency of the motors. The products that were evaluated, 10 motors, premium efficiency IE3, 40 to 100 horsepower, low voltage, totally enclosed fan cooled. They were all low voltage. Low voltage meaning any motor that's rated up to 1,000 volts. And they were 50 hertz and 60 hertz. Because we were linked up with our friends across the pond in the UK, we had 50 hertz motors as well as 60 hertz motors. NEMA machines and IEC machines, 2-pole and 4-pole motors. The test method that was used is called IEEE 112 Method B, which is a dynamometer test. And that is harmonized with the IEC test standard for efficiency, IEC 60034-2-1. And Advanced Energy is the only independent NAVLAP accredited test facility. NAVLAP is the National Voluntary Laboratory Accreditation Program. And when we say independent, what makes them independent is that simply they are independent. They're not, they stand alone. What's not independent would be the motor manufacturers themselves. The motor manufacturer builds the product. They have accredited labs that they can go back to the Department of Energy and say, we've tested this in our lab, and it is as efficient as we're showing on the nameplate. It meets the Department of Energy requirements. And the testing that's done, whether it's done at a motor manufacturer lab or at Advanced Energy's lab, for example, if 3 different labs tested it, the equipment test repeatability, they'd find that the efficiency value that it's obtained, they're all within 0.2%, 0.2%. That's actually pretty phenomenal if you think about it. The methodology, each motor was load tested and was put 100% load, tested for efficiency before and after rewinding. They were rewound at an accredited service center. So one of the EASA accredited service centers did the rewinding. And the key details of the winding that were addressed, turns, length of turns, wire area per amp. The factors that could change things like winding resistance or winding magnetic turns could change the core losses by changing the magnetic strength. Also, bearings, we were trying to focus on changes affected by rewinding work. So bearings weren't replaced, lubricant wasn't changed. The bearings were wrapped, the end brackets were wrapped, the rotors themselves were wrapped, everything was wrapped up and stored while the winding work was done, so nothing was disturbed. The rotors weren't even balanced. We didn't want to change anything there. We don't want to introduce anything that would make a change other than the windings and the cores. So the most important test result, let's call it, it's the bottom line. It's the post-rewind efficiency versus the pre-rewind efficiency. What was the change? The range of values, some motors, one motor was as high as a 0.3% efficiency gain. Another motor at the low end of the spectrum was 0.5% reduction in efficiency. Very narrow band, very small change in losses. The overall change out of the 10 motors, an average of 0.1%, which that in itself is within that test method range of 0.2%. So really overall, very, very small change. Summary results, here's the 10 motors alphabetically labeled. These were randomly labeled from A to J. So we have these test results, and I'm not going to go through the test results just to display. But if we look at the far right column, the post versus pre-winding, you see the top one happened to be the plus 0.3 gain, and we've got 2 that had a gain and 2 that had no change at all, 0, and then the remainder had some slight loss. So the net change was 0.1%. Sometimes I again, going back to my days working in a service center and selling electric motors, you know, can we believe the manufacturers that they really, you know, the nameplates meet what they say they have? Well, pre-rewind versus nominal, this is the manufacturer's changes. They're within 0.2% of what they're saying their efficiency should be. So it says, can you believe the motor nameplate? I think, to be honest and fair to the manufacturers, yes, you can. By the way, all of these values, they're efficiency values in percent. And if you want to do some deeper diving, motors E and H are the same rating from the same manufacturer. They're identical. Motors I and J happen to be the same rating, but they're from 2 different manufacturers. So just, you can see pre-rewind by test, 93.1, 93.6. If you knew that from the nameplate, and I wanted to buy a motor and make sure I'm going to get my big payback, I'd be picking the one at 93.6. So, conclusions from the rewind study was that rewound premium efficiency IE3 motors maintained their original efficiency. It affirmed that the good practices in AR100 and the accreditation program, the ones that are used in the program, that they are effective.